Eigenvector centrality represents one of the most fundamental ways in which we will assign importance of nodes in a network. And so for that reason, we're going to take the time to appreciate both an intuitive way of thinking about eigenvector centrality and also analyzing it mathematically. So as we move away from just using degree as a way of determining a node's importance, eigenvector centrality uses both essentially how many neighbors a node is connected to, which is the same as degree centrality, but it also includes how important that node or those neighbors actually are. And so a node could be more important because it's connected to fewer but more important other nodes. And so that's the basic idea of centrality. And our intuitive view comes from the idea of passing centrality around. And so if our centrality vector is the vector x, then the idea of passing things around means moving along the edges of the network. And so that means that we'd be multiplying the centrality amount x, which is contained in this vector x, and we're multiplying it by the adjacency matrix to push it forward. And that we would store into the variable x again. So we can write this as this process where t indicates the time. And so this means that we keep iterating, we increase time, or you could think about this as iterations. And so we take our initial value of x and we multiply it by a, and we store that as our new value of x. And then we just repeat this process. And so if this converges and has a steady state value, then that means in steady state you have this special vector x, v, which is the special version of x. So in steady state, x trends to this vector v, and v is such that in steady state, when I multiply v by a, I get v back again. And this is this idea of a steady state. And so this is the idea that the amount of centrality that x1 has gets passed to x2 and passed to x3 at the next time step. But x3 also passes its centrality to x1, and x2 also passes its centrality to x1. And so that means this steady state implies that in the new time step, you're both giving away and receiving the same amount of centrality. When we model this mathematically, we still use this idea of this process. And what we're going to do is we're going to look at what happens to x of t as t goes off to infinity. And so this is a recursive equation because it's defining x at t plus 1 in terms of x at t. We can aggregate this together and say that this is going to be a times dot 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 all the way down to a times x. And then this implies that there are going to be t copies of this A matrix. And that's just because at each time step we're multiplying by A. And this x here, I'll call this x of 0 because it's our very first initial 0. So in this analysis, we're going to consider undirected graphs. And so that means that the adjacency matrix A is going to be symmetric. And one of our very useful facts from linear algebra is the fact that a symmetric matrix has eigenvectors that span the space. So they span Rn because this is an n by n matrix. And that these, by spanning it, it means that they're also linearly independent in this span. And this is, you can kind of think about this as the fact that we can use the eigenvectors of A as a basis to represent all other vectors that live in this space, which is the same idea as thinking about our standard XYZ axes and the fact that any point here we can represent as a combination of points as XYZ, and we can do so uniquely. And so that's the idea. It's the generalization of a basis, which means that says that any vector u can be expressed as a combination, a linear combination of the eigenvectors. And so these c's are just constants that tell you what they are. In terms of our XYZ coordinate system, these coefficients are the coordinates. What does that mean in the context of eigenvector centrality? It means that if we have if we notice that x of 0, our initial centrality guess, is in Rn, that we can also represent that in terms of the eigenvectors. And so we're going to use this expression not because it's clean, but because it allows us to say something about what happens as t goes off to infinity, because we know something about the eigenvectors and eigenvalues. So if we represent x of 0 in the same way that we did here for the vector u, that we just represented as a sum of constants multiplied by the eigenvectors, which means that if we rewrite this expression, we get this, where this term is simply just x of 0. If I move this a of t inside, this is just a sum, so it's just distributing a of t, a to the t, through that sum, then you see that we get all of these terms, a to the t times vi. And the important thing is that vi is an eigenvector of a. And remember that that's lambda v is equal to a times v. This is the eigenvalue-eigenvector equation. So anytime you see AV, you can replace it with lambda times v. And notice what happens is if I do this twice, AV becomes a times lambda times v, and then that's lambda AV, which becomes another copy, so I get lambda squared v. And so for as many copies of A that I have, I get that same number of copies of the eigenvalue. So that simplifies to this new sum. And now we're going to use another fact from linear algebra, and this is summarized as on the slides following this video. It's the Perron-Frobenius theorem, which tells us that there is a largest eigenvalue and that all of the other ones are going to be smaller in magnitude than it. And so what we're going to do is, from this sum here, we're going to extract the largest one, which I'm going to call lambda 1. So that's this term. And then in all of the other terms, I'm going to pull out a copy of lambda 1 to the t. Remember, this is the largest eigenvalue. And by pulling it out, that means that inside this element here, I'm going to divide by it, so it cancels. Essentially, that this would cancel with this. But if I keep it there, then what this says is that all of the contributions of all of the other terms are going to go to 0 as t goes off to infinity, because lambda I is going to be smaller than the largest eigenvalue, lambda 1. And so this term is less than 1, or sorry, without the t. This term is less than 1, and so when I take it to the t power, as t goes off to infinity, this becomes extremely tiny. And so that means that as t goes off to infinity, the solution is just dominated by this particular factor, which is characterized by the eigenvector and the eigenvalue of the largest eigenvalue of A and its corresponding large eigenvector. And so this C is just the constant coefficient that depends on the original choice of x of 0. So the important part is that this is a number, even though it may be changing with t, this is a number, and this is a vector. So we saw that as t goes off to infinity, the centrality, following the update rule that we just multiply it by a each time, we get a centrality that looks like this. Because we only care about the relative centrality values, that we don't need absolute values, that we can just ignore this constant that's out in front, and we just consider that the centrality is indeed the eigenvector that corresponds to the largest eigenvalue. And this is why it is called eigenvector centrality. One last thing I want to point out is the fact that if we look at the eigenvalue-eigenvector relationship, this is this nominal equation, if we rearrange this and I say that this is x and this is x, what this is telling me is that x is equal to 1 over lambda 1, so 1 over the eigenvalue, times a times x. And so if we look at so this is the vector version of that equation. If I look at a specific node I, then what I'm doing, I'm rewriting this as a matrix multiplication. I'm writing this in terms of a sum, and so if I leave out this term, then this is simply just a sum of the centralities of all of the other nodes that that have an edge with node I. So all of the neighbors of node I, we sum up their centrality, and that's what the centrality of node I would be. And so this gets back to this intuitive way of thinking, is the fact that we do have to keep this term in there, so we have to divide by the largest eigenvalue, but the idea is that if I take the sum of all the centrality values of my neighbors, essentially everything they're going to pass to me, that is equal to the centrality value that I have. All right, so there's that intuitive idea of swapping centralities, and then we get to a point where you're giving out and taking in as much centrality. And then remember that eigenvector centrality is really this idea, is that the centrality can be large either because it has a high degree or because it's connected to nodes that have a large value of xj. So this sum can be large either because there's many terms or because several of the terms are quite large.